Hello, guys. In this chapter, I'm gonna go over chapter 14, and so far we've covered chapter 12 and 13. This chapter is about relating or about developing basically the concepts of work and kinetic energy. And long story short, this chapter simply, the heart of this chapter is the following equation, which is a change in kinetic energy of a particle. Is equal to the work of the external forces which are applied on an object, right? And the change in kinetic energy is given by 1 over 2 mv2 squared minus 1 over 2 mv1 squared. And the work of a force is given to you as F times ds. All right, I can rewrite this relationship as, so the initial kinetic energy of the object, 1 over 2 mv1 squared, plus the work that is done on an object by net external force, Ts, must be equal to the final kinetic energy of the object. Now, if the net work applied on an object is positive, it means that my final kinetic energy will be greater than my initial kinetic energy. And if the net work applied on an object is negative, it means that my final kinetic energy will be less than my initial kinetic energy. And by definition, kinetic energy is simply 1 over 2 mv squared. All right. If you now, let's actually take a look at what we have in our lecture. Okay. All right. So this is chapter 14, and then this is already posted on Blackboard. So the goal of this is to be able to calculate the work of any force, and then to apply the principle of work and energy to be able to find either the displacement, the velocity, and the force that is actually applied on an object. In the case of this roller coaster, basically, if I were to look into the final velocity of this object after it is released from A into B, then I can also apply the same equation with it, which I just did. Right? How can I do that? So I know my delta Ke is equal to the work of external forces, or I know my initial kinetic energy plus the work of the external, of all the external forces here, not just one, all the external forces are going to be equal to 1 over 2 m v2 squared. In my case, let's say this guy was released from rest, so v1 is going to be 0. What is the work of external forces? So in the case of gravity, right, if gravity is applying a force that is along the motion, then it will be positive, right? If gravity is applying a force that is opposing the motion, then the work is going to be negative, right? So the work of gravity is also independent of the path taken. So it does not actually matter the path, right? What actually matters is simply the vertical displacement. So in that case, I know the work of gravity must be positive, right? So mg multiplied by h, right? Where h is that distance, is going to be equal to 1 over 2 v2 squared. So now I can actually find that velocity. So I know m and m will actually cancel out. So v2 is going to be equal to square root of 2gh. All right. And now let's say if I ask you to find the normal force that is applied on that object at point B, how would you calculate that? Again, normal force applied at point B, given that you have a radius of curvature of rho. Now, what you want to do is you want to apply what we did actually in other chapters. We want to do a simple basic free body diagram. How would the free body diagram look like on here? So at point B, right, this object will have mg, that is its weight, and then we're going to have a normal force and applied on it. And on this diagram, we're going to put the accelerations, and then I know this guy is going to be equal to what? M v2 squared over radius of curvature rho, right? And then you get v2 from here. So here we have used two different things so far. So we used the conservation of kinetic energy or the principle of work and kinetic energy to be able to find the velocity at the second point. And then we're using summation of forces to be able to find the normal force applied on the object, right? And now if I, sum the forces in a vertical direction, I'm going to get N minus mg is going to be equal to m v2 squared over rho. So my normal force is going to be equal to mg plus v2 squared over rho. All right. Okay, this has so many applications. You know, usually you want to use this concept to be able to get quick answers, right? Without actually having to find, you know, differential equation, or, you know, find a as a function of time or velocity as a function of time, integrate that, find the distance as a function of time, etc. You can use that to get like just aggregate numbers that you may find useful. So in the case of this thing here, if you have a so these barrels are used to decelerate cars right off the highway, and we can use that to estimate, you know, how many barrels we need, for example, to be able to slow down a car. And what we do is actually we're going to apply the same thing that we did before. We're going to apply the concept of work and energy. So how we do that basically? You know, let's see. You know, let's apply this to see, you know, what is the distance that is needed to basically obtain a particular force that we apply on a car. We want to minimize the force that we apply on the car to actually decelerate that. So if we actually use that, difference in kinetic energy is going to be equal to the work of external forces applied. What is the difference in the kinetic energy here? The final minus the initial, right? The final is 0. Initial is going to be minus 1 over 2 mv0 squared, right? So this is a velocity at crash. Work of the external force, I know that the force here is going to be opposing the motion, right? So ultimately it's going to be on average, right? So, okay, I can do this minus f times dx, right? So here, obviously, I need to know the force as a function of displacement. So, you know, these are the barrels, let's say, right? So this is my d here. I would need to know exactly the force as a function of this variable d, right? So if I'm here, what is the force here? So if I actually took this as an average, I can say minus average force mazboot times the total distance, right? And I know minus and minus actually disappear. Now I can either find, you know, the distance that we need, or I can find the average force based on that velocity. So this is locked. I can control these guys, right? If I increase the distance, what happens to the force? It will actually reduce, right? So D is going to be equal 1 over 2 mv0 squared over the average force, right? So the less the force that I want to produce on a car, and the greater the distance. All right. So, and one basic equation, basically now you are able to, you know, conclude valuable information on that. And then if you are wondering where this relationship actually comes from, it simply comes from you know, this relationship. We remember we had a ds is equal to vdv. Remember that relationship. Ads is equal to vdv. If you multiply both sides by m, you get mads is equal to vdv, right? But what is ma? I know ma will always be equal to the net force applied on an object. F external ds, here it's mapped along the distance, m vdv. If you integrate these two, and the work is going to be equal to here the change in kinetic energy. Change in kinetic energy. So it comes from this ADS equal to VDV, and that is what that slide is about. So we've already described all these. So if you have so many forces, you would basically have the work of all the forces. So it's summation of all the works, right? You know, if, for example, what would be the work of the normal force? It would be 0, because the normal force is always normal to the motion, right? And if you are normal to the motion, you cannot move an object along the motion. Work of friction will always be negative, right? Because it's always opposing the motion. And you know, any other force that you have, you will simply have to project that force along the motion by multiplying it by cosine theta, right? And this actually will come naturally as you are doing the work of FR. If I was doing the work of FR along ds, so it's going to FR as a vector times ds, right? FR times ds is going to be equal to, so in that case, if I were looking at, you know, the work of FR is going to be equal to FR times ds, right? FR times ds is going to be equal to FR times ds times cosine theta, right? From 0 to s, or from, you know, s1 to s2, whatever it is. But here theta might change, right? And then ds is changing, so you need to relate ds and then theta. Well, most of the problems we're going to be dealing with, they don't involve it, but if they do, then you will be able to actually relate the ds and then theta. Like, you know, if you are actually sliding on a circle, you will be able to, you know, relate the position by the theta by knowing that ds is equal to r d theta, right? I think there's a problem like that in the assignments that I want you guys that you can, you know, take a look at. Okay, okay, that is really it regarding that. Okay, F is TS cosine theta. Okay, very simple. Regarding the work of gravity, remember I said earlier that, you know, no matter how you are moving, if you actually have gravity, it doesn't really matter, right? If I were to look at the work of gravity from point A to point B, I will simply consider that H, right? Why is that? It doesn't really matter, you know, the motion doesn't matter, and really, if the reason why this is true is because of the following, right? If you integrate, so the work of gravity from, you know, let's say A to B, right, is equal to the integration of F times dr. I can always replace F by minus mg times, in this case, we have y going up, so minus omega mg times j, right? Here, minus mg times j times dr. What is dr? dr is going to be equal to, I can decompose this movement into a Cartesian, dxi dyj plus dzk. And I know that product of two vectors which are 90-degree apart, it will be 0, right? So j times I will be 0, j times j is 1, and then j times k is 0. So you actually only end up with this vertical component, right? So any movement that is not in, that is in the I, for example, direction, will actually not create any work, right? And the gravity don't create any work in that direction. It only create a work in a vertical direction. Does that make sense? So ultimately, the work of gravity will be mg times h. Okay, more long, even more simplistic. You know, if I have an object going down, should work of gravity here, the gravity is helping me, مظبوط. So mg times whatever displacement I did. If I'm lifting it up, then the gravity is going to be doing negative work. Okay, same thing applies for all the forces. Okay, now let's look into the work of a spring. Okay, and this is the most tricky part in this chapter, but you know, just pay attention exactly to what I'm doing here, and I think you will find it very easy. So every spring will have a free length, okay? So if you know, if you go, you know, if you are, you know, messing around with some mechanical object, you will get a spring, and then when you get a spring, it will always have a free length, okay? If you don't mess with it, the spring will not apply any force on you. مظبوط. You just hold it like that, right? It's not going to apply any force to you. But the minute that you try to apply to compress it, it will apply a force that opposes you. مظبوط. If you try to stretch it, it will also apply a force that opposes you. But here, assuming you're starting from the free length. If I actually have a reference frame X that I'm using, if I was here, how is the force, right? If I'm greater than L0, I know the force is going to be like that, right? You agree? If I was here, if I was before this guy, before the free lens, then the force is going to be like that. Okay? So, and I know the force of the spring is going to be related to the stiffness of the spring. So I can actually write this force to be equal to what? Minus k times x, mathematically. If x is positive, then I know the force is going to be in the opposite, in the negative direction. مظبوط. If x is positive, then this guy is good. Right here, the natural positive is to the right, is along x. Now, if I was here, right, is that true? Also, minus kx, does it also apply here? If x is negative, right, minus times minus is positive, so I actually get the right sign of the force. So the force will actually always be equal to minus kx on a spring, assuming that you are doing this x is like that, and assuming that x is starting from equilibrium. You can always write that the force of the spring is minus kx. X is positive, you're in the opposite direction, right? X is negative, you are in the opposite direction. So here, if x is equal to, let's say, 0.1, I know that the force is going to be in that direction, in the I frame. Does that make sense? I can even put I for you guys to just to, okay? All good? Now let's actually look at the work of the spring. So the work of the spring is equal to what? Is equal to F times dx, right? And I know dx is in the I direction. This guy is in the I direction, so we are good. So we're gonna write, so what is F is equal to minus kx multiplied by dx. And I'm gonna write that from x1 to x2, okay? What is the integration of this guy? It's gonna be minus kx squared over 2, x1, x2. And you know, those of you who are math savvy, they know that, you know, if you basically multiply this by minus, you can basically switch those two, right? It will be kx squared over 2 x2, x1, right? And what is that going to be equal to? It's going to be equal to k over 2 k x1 squared minus x2 squared. So the work of the spring is going to be k over 2 x1 squared minus x2 squared. But let us actually take a look into it in more detail. All right. Let's come back into this, and let's say, you know, that's your friend, your spring. Okay. And you know, let's say this is your free length of the spring is actually here. Okay, this is my L0, so X is measured from here, both. So X will actually begin to be measured from here. Let's actually increase that. So if I told you that, you know, X1 was here, okay, so initially you started at X1 and you ended up at X2. What do you think the work of the spring here is going to be, negative or positive? Well, let's rewrite that. What was the work of the spring? Was equal to k over 2, and this is what I just wrote before, x1 squared minus x2 squared. So if x1 is here and then x2 is here, then x1 is less than x2. You guys agree? So in this case, x1 is less than x2. Then the work of the spring is going to be what? Negative. Okay, which makes sense. Basically, the spring is opposing your motion, right? As you try to actually pull it from here to here, and the spring is actually opposing your motion. Now that's actually, let's say, and you know, I'm just going to simplify that, and I'm going to just tell you that obviously this guy is my L0, right? Let's do it over, like, you know, several intervals. So this is always the free length of the spring right here. Okay, if I actually if I started at x1 was here and x2 is here, what do you think the work of the spring? So just, we're looking here at the absolute value. So if x1 is greater than x2, right? So this value here, x1 is greater than this value, right? This is my x1, this is my x2, then the work of the spring is going to be positive, right? Why? Because I'm moving from here to here. The spring is actually helping me out. Now let's actually do it here. If x1 was here and x2 was here, then the work of the spring, do you think is going to be negative or positive? Now notice this is a compression, right? So the spring started like this. Okay. Now, is the work positive or negative? The work is positive. Why? Because just look at this equation. Okay, this is the absolute value of x1. Absolute value of x1 is greater than the absolute value of x2. So the work of the spring is positive. All good. Now, if x1 was here and then x2 was here, basically you are compressing the spring, then the work would be negative. Now let's actually look into this. If x1 was here, negative, and then x2 is here, what do you think the work of the spring is going to be, negative or positive? Well, it's negative. Why? Because just look at the absolute value. So you're simply comparing this x1 with this x2 and then only as absolute value, right? So x1 is here less than x2, right? So the work of the spring is negative. So long story short, you just need to, when you want to find the work of the spring, just look up at this equation, right? And you know, all what you are looking for here is the distance to the equilibrium position, right? Remember, x1 is measured with respect to the equilibrium, x2 is measured with respect to the equilibrium, and the work of the spring is going to be all of this guy. Okay, work of gravity will not matter, right? Work of gravity, we'll break down that. So in this course, mainly we'll deal with the work of springs and work of gravity, right? When we are evaluating the kinetic energy, and also work of frictional forces. Okay. What I want to do right now is we're done here. I'm just going to do example 1, and we're going to be good to go. All right. So we have 100 kilogram crate, right? So this is your crate, and we have 400 Newton force applied on it in that direction. So 400 Newton at 30 degrees, and then I have 500 Newton, and this guy is at 45 degrees. And I know the mass of this guy is equal to, well, obviously this is your ground. The mass of this guy is 100 kg. And if it is originally at rest, we need to find the distance it slides in order to attain a speed of 8 meters per second. So it's initially at rest, and then we want to find the distance, d, that this guy will travel before it actually reaches 8 meters per second. And then they told us the kinetic friction is going to be coefficient of kinetic friction equals 0.2. Well, what we'll do is let's put all the forces that are applied on this object. and then we will do their work, and then we'll apply the concept of, you know, total work applied on an object is equal to the change in kinetic energy. I know the change in kinetic energy will be simply to the final kinetic energy because the initial kinetic energy here is 0. So what are the forces? I have N, I have my weight, مظبوط, and I know my friction is going to be opposing the motion. It's going to be equal to mu k times N because it's already moving, so mu k times N. Okay, so what is the equation that I'm going to write? I'm going to write that so initial kinetic energy 1 over 2 mv1 squared plus the work of all the forces, right? Summation of all the works is equal to my final kinetic energy. مظبوط. So initial kinetic energy is 0 starting from rest. Final kinetic energy V2 is equal to 8. Mahiki, we have the mass, so we just need to find the work of all the external forces. We'll just start at them one by one. What is the work done by this guy? So you're going to project it along the movement. The movement is horizontal. Work of the 400 newtons is going to be equal to how much? 400 times cosine 30 times d, right? You want to multiply it by the distance. How about the work done by the 500? It's going to be also 500 times cosine 45 degrees times d, right? We're good. How about the work done by mg is 0 because mg is perpendicular to the movement. Work done by n is also 0. What about work done by friction? Well, we have to incorporate that. Minus, right, because it's opposing the motion, mu k times n times d is equal to 1 over 2 mv2 squared. So we have all of these. We are trying to find d, but we don't know n. How can I find n? We sum the forces in a vertical direction, and I know that n minus mg, right, minus 400 sine 30 plus 500 sine 45 is equal to 0. Now you have your friend n is equal to mg plus 400 sine 30 minus 500 sine 45 degrees. So we have our n. Continue, and then we find d, right? So I'm just gonna separate d, and then I'm gonna write 400 cosine 30 degrees plus 500 cosine 45 degrees minus mu k times n, which is equal to mg, which is 100 times 9.8 plus 400 sine 30 minus 500 sine 45. Okay, another parenthesis equal to 1 over 2 100 times 8 squared, and I will let you guys plug this in your calculator and divide this guy over this guy, and then you can find the distance. Okay, guys, so that is it. Make sure you go over this video very well. Make sure you understand the work of springs very well, and make sure you understand why the work of gravity is independent of, you know, any dy or dz move, or, you know, any other movements but the vertical movements. And make sure you know that when you are calculating the work of a force, you always have to project it on the movement, right? So it will be, that is why we have a dot product. So meaning that you have f times cosine theta times the distance, or the derivative of the element of the distance before you integrate that. Okay, guys, any questions, by all means, please email me, and I'm very happy to schedule a one-on-one appointment to actually discuss any of that with you guys. Okay, usually the afternoon works best for me than in the morning. Thank you, guys, and have a nice day.